Okay, thank you very much to the organizers for the chance to speak. So yeah, I'd like to talk again about this idea that we've heard already a bit today about generalized symmetries, which are some perhaps more categorical notion of symmetry in quantum field theory. And whereas Sakura's talk this morning tried to understand some of the geometry associated to these symmetries by engineering quantum field theories using string theory in geometric engineering, I'd like to take a slightly orthogonal approach here and try to attach some geometry or some geometric meaning to these generalized symmetries much more directly in quantum field theory by studying the geometry of their moduli spaces or vacua and trying to find some slight enhancement of those structures that is capable of capturing these generalized symmetries. And so this is kind of part of a series of work on these topics about thinking about generalized symmetries in this way with Lakshya Bhardwaj and Andrea Ferrari and Sakura as well. Okay, so let me just begin with an introduction. Hopefully I'll give you an idea about what the broad picture is and where we're going with this. And so, yeah, as we've already heard, there's been a kind of a development in the notion of symmetry in quantum field theory, namely that it's a bit more broad than we originally thought. And in the last 10 years or so, there's been a kind of a resurgence in study of these symmetries where we try to approach this topic more systematically and understand the symmetries and perhaps their anomalies in a much more systematic way. And the stack is something that captures that extra little bit of data. So in particular, the kind of fiber of this map is something that captures the existence of some TQFT. Are we okay, Cyril?
Yeah, that's fine. It was the recording.
Okay. All right. And so the basic idea is that the generalized symmetries, in particular higher groups, they will act naturally on this moduli stack that captures this extra pieces of information. Okay. So what's the plan? I'm going to focus on a very particular class of supersymmetric theories, namely in 3 dimensions, and also with what's called n=4 supersymmetry, or 8 supercharges. So it's the same amount of supersymmetry that was talked about this morning in Sakura's talk, but in 3 dimensions rather than 5. But I expect that the general idea and the general structure should apply with some differences, caveats, generalizations to also theories in other dimensions with the same amount of supersymmetry, or perhaps even with less supersymmetry. Okay. And so I'm aware that this is a mixed audience and that there are mathematicians and physicists. So my strategy is going to be to ply you with examples rather than try to give general structures. And then hopefully you'll be able to latch on to something within those examples and follow them through. We'll see how it goes. So I'm just going to go straight ahead and talk about examples of field theories that have these kinds of structures and how we think about them. All right, maybe I'll stop and see if there's some questions first about this. Yeah.
Why might be being a stack instead of your interpretation of the
I have no idea how to answer that question. I'm sorry. I don't know. Sorry. Yeah. Yeah. I think fundamentally it's the second picture, but that's not the way that physicists would normally think about it. It will be the first picture.
So X has got nothing to do with space-time.
No.
X is some internal.
No, that's right.
Space that
yeah.
Things are carrying around.
Something like that. Yes. Yes. X is not space-time. It's like, if you like, you could think about it as the target space of a sigma model. Might be one way to follow through this lecture. Another way, I mean, that might be another point of reference that might be slightly helpful. One way to think about this story is that just to connect to space-time, if I'm in 3 dimensions, I can think about a theory of maps from my 3-dimensional space-time into this target space X. That's what we would normally call a sigma model. Well, if we're considering a sigma model into a stack, it's a bit like discussing a gauge theory, something with a discrete, perhaps with a discrete gauge symmetry involved. That might be another point of reference and way to follow through.
The first way you wrote ought of curly X. The ought is a higher group.
That's right, indeed. So that's the basic thing underpinning this, is that if you look at automorphisms of stacks, you get a 2-group. Or higher stacks, you get higher groups. Yes, exactly. Okay. More questions, or I'll dive in with an example. Okay. So I'm going to tell you about a theory which physicists call supersymmetric QED. So this is an abelian gauge theory. The gauge group is U1. And in this context, we say that there are n hypermultiplets of charge 1. I'll tell you in a bit more detail what that means in a second, but there are n charged fields, all of whose charge is 1 or minus 1. And it has a bunch of symmetries. It has one symmetry that might be obvious, called the flavor symmetry F. And that's something that's going to rotate these matter fields. In 3 dimensions, there's also something called the topological symmetry, which I'll explain a bit more what that's about later. And it's also important to not just talk about what the symmetries are, but what are their Tuft anomalies. And the way to think about that is that a Tuft anomaly is like an obstruction to gauging the symmetry consistently. And they can be specified by what's called an SPT phase or an invertible TQFT. I'm not going to explain in too much detail what that is, but I'll explain a bit more about what this means. But these symmetries have a Tuft anomaly. Okay, so let me explain how to think about this. So this theory has some scalars in it, some scalar fields, complex scalar fields that I call x and y. And they have an index that runs from 1 to n. And x has charge 1 under the U1 gauge symmetry, and y has charge minus 1. This is what roughly we mean by there being n hypermultiplets. And the first thing that we're interested in, if we want to study the symmetries of the theory, is to study what local operators we have. And so the first thing to ask is, what are the genuine local operators? So the things that are really honestly supported at a point in space-time. And these have to be gauge invariant. You have to build combinations which are invariant under the U1 gauge symmetry. And one way to do that is to build these mesons. So we take a product of an x and a y. One has charge minus 1 and one has charge 1. And if you look at these mesons, well, they transform in the adjoint representation of the Lie algebra SUN, which acts by conjugation on this meson matrix. It's by conjugation by n matrices. And so what that means, and basically all local operators are built in some sense out of operators of this type. And what that means is that the symmetry group that's acting faithfully on the local operators, well, it's a Lie group whose Lie algebra is SUN, but the group that's acting faithfully is P of SUN. That's because in some sense, everything is built out of the adjoint representation. So the flavor group is PSUN, and it acts on the local operators. And we can introduce, whenever we have a flavor symmetry, we can always introduce a background field. So this is like a background connection, a one-form connection. Or if you like, you can think about it as a homotopy class of maps from space-time, M3, into the classifying space of the group. Okay, so the flavor group is P of SUN, but just like in Sakura's talk, we will also need to discuss not just genuine local operators, but local operators that also sit at the end of line operators. Another way to say that is that the local operators screen the line operator. And it's a general feature that if you study not just the genuine local operators, but those that sit at the end of a line, they may transform in a slightly larger group. You may need to pass to a larger group, an extension of the group, in order to capture all of the representations that arise. So let me do the following. Let me consider some Wilson lines. So Wilson lines are things you build out in the gauge theory by studying the holonomy of the connection, the gauge connection in some representation. So the gauge group here is U1. So the Wilson lines are just labeled by an integer, n. And a basic feature about Wilson lines is that whenever a Wilson line ends, the things that sit at the end of it have to transform in that representation of the gauge group. So in particular, if I want a Wilson line of charge n to end, then I need it to end on something with gauge charge n. So what are those things? Well, I can take basically any homogeneous polynomial in the x's or the y's, depending on whether it's positive or negative, of that given degree. So in particular, in the picture, if I take just the Wilson line of charge 1, it has to end on operators of charge 1. So I could take any, I could just take any of those fields X. But now the symmetry algebra, SUN, will act on those things in the fundamental representation, if it's W1, or powers of the fundamental representation. And so what that means is that if we want to accommodate the charges of these local operators, we need to pass to a slightly bigger group. We need to pass to an extension, central extension, which is SUN. And that's important in this story for a variety of reasons, for studying Tuft anomalies, but also for studying whether this can participate in higher groups later on. Okay. So that was one of the symmetries. There's another one in this game, which is kind of special to 3 dimensions, or at least the fact that it's an ordinary symmetry is special to 3 dimensions, and that's sometimes called the topological symmetry or the magnetic symmetry. And the idea is that this is a symmetry whose charge is basically measuring the magnetic flux through a 2 surface. So in particular, the operators that are charged under this symmetry, on which this symmetry acts, are called monopole operators. And they have the property that if you take a point where the operator is inserted, you surround it with a 2-sphere, and you compute the magnetic flux through that 2-sphere, then it's quantized to be some fixed integer m. And that's the weight of the that's kind of by definition the weight of the representation under this symmetry. And so again, corresponding to that, just like before, we can introduce a background field, a one-form connection on a bundle, or if you like, a class of maps from space-time into the classifying space of the group. Okay. So let me now discuss, so we have these 2 symmetries, but they actually have an anomaly, which means that you can't gauge them both simultaneously in a consistent way. So let me try to, I don't want to give a very detailed answer, but let me give you an idea of what this anomaly is kind of capturing in terms of these pictures. So there's an important point here, which is that these Wilson lines can also be thought of in a different way as vortex lines for the topological symmetry. So in particular, if you have a Wilson line of charge n, it actually requires the background field for the topological symmetry to have a kind of singularity along the line. In particular, if you integrate it, I didn't draw a picture here, which is very bad. So the picture looks something like this. You've got a line and then a small disk, D2, that intersects the line. And so what the Wilson line does is it forces the background field to have well, it forces there to be a kind of flux supported along this line for that background field. So we call that a vortex line. Yes.
In space.
That's in space. Yep. That's all sitting inside of space-time. Yes.
The issue you're saying is that it must transform some.
Yeah, that's another way to say it. Yeah, is that yes, exactly. It imposes a fixed holonomy around this. If you go around a small circle around the line. Yeah, that's right. So let me not give an argument why that's true, but just ask you to accept it as fact. But then we get an interesting feature, which is that these operators, which is essentially just a restatement of the previous slide. Oops. Or this slide here, the fact that we needed to pass to SUN bundles, to SUN, the extension of the flavor group. One way to say that is that generically these Wilson lines or these vortex lines will end on local operators that transform under the extension, under SUN. So they're charged under the center of SUN. But they can only end on operators that are not if n is 0 mod n, so if it's a multiple of n. And this is actually a statement of a Tuft anomaly. It means that you can't simultaneously gauge these two symmetries. And so let me just give some broad features. I mean, you can see here that the anomaly depends on the flux here, mod n. It's kind of what you'd expect given this property. And W2 here is the obstruction class that's obstructed. We had this background bundle, a PSUN bundle. And W2 is the class that obstructs lifting that to an SUN bundle. And again, that's what you'd expect given this property. So these guys have a mixed anomaly. So the challenge now is to try to express these ideas geometrically. So to understand where these symmetries come from in terms of some moduli space X, and how to think about this Tuft anomaly. So let me try to do that. So let me first consider the local operators. So I'm going to go through the same steps, but translate into geometry. So let me first look at local operators. Well, we've already seen that if you want to make them gauge invariant, you need to take bilinears. So we can just put them in a matrix, an n by n matrix. And I slightly lied before. They have to obey a further constraint, sometimes called the F-term constraint or the moment map constraint, which basically tells you that, well, it implies that the trace of this matrix M is 0 and that it's also nilpotent. And so another way to say that is that the local operators are functions on what physicists call the Higgs branch of the theory, which in this case, well, these equations describe algebraically the closure of the minimal nilpotent orbit in SLN. So this is the moduli space in this case. And we can think about local operators as functions on the moduli space. So if the symmetry acts on the functions, it's going to act on the space itself. Okay. So this moduli space is singular. It's conical, and it will be nice to resolve it. So let me explain how to resolve it, or how to see the resolution. Well, the resolution is exactly the thing we see when we study local operators at the end of lines. Okay, so again, if we consider a Wilson line of charge n, it can end on homogeneous polynomials in these coordinates, the xj's, of degree n. Another way to say that is that I can resolve the Higgs branch and then study sections of line bundles, and I'll recover exactly the same things. So what this tells me is that I can think about these line operators, the Wilson lines, I can think about them as line bundles on a resolution of the moduli space. And the local operators that sit at the end of the lines are sections of those bundles. Okay, so in this case, the resolution is given by the cotangent bundle of CPn-1, complex projective space. And the bundles you get corresponding to these Wilson lines, the things whose sections are described by local operators at the end of lines, these are just obtained by pulling back the standard line bundles on the base to the space. And so hopefully the fact that sections of the line bundle ON involve things like homogeneous polynomials is familiar. Okay. Good. So let me then give a geometric interpretation of the facts about the symmetries and the anomalies of this theory. Okay, well, first of all, we've got our Higgs branch moduli space resolved, which is this cotangent bundle to CPn-1. And the flavor symmetry, F, which is PSUN, is the thing that acts faithfully by isometries of this space. So I should be a bit careful here. These are these are isometries that preserve the symplectic form on the cotangent bundle here. But okay, they act by isometries. On the topological symmetry is a bit slightly more intricate to understand, but the topological symmetry comes about from studying the topology of the Higgs branch, in particular of the resolution. And so in particular, you can think about the topological in the symmetry in the following way. Its charge lattice is the second cohomology of the resolved space. So in this case, if the target space is just CPN, T star of CPN minus 1, that's just a copy of the integers. So the symmetry is U1. These are just the Wilson lines, really. If you want to think about this from a physical point of view, if you think about the theory as a sigma model into X, then you can always take a class on the target and you can pull it back via this map and integrate it to get a topological defect. And that's the topological defect that generates the zero form symmetry. It's another way to view this second statement. Okay, well, the Tuft anomaly is now easy to interpret. It's just a statement that if you look at we have these line bundles, we have an action of a symmetry on the space, and we can ask if the bundles are equivariant with respect to that symmetry. And the Tuft anomaly is just the statement that they can't all be made equivariant. They can all be made SUN invariant, but they can't quite be made PSUN invariant. That can only be the case if n is not equal to 0. So the Tuft anomaly is capturing properties of whether line bundles on this space can be made equivariant with respect to the symmetry. Okay, that's all I wanted to say about this example. So I'll stop and see if there are some questions. Otherwise, we'll head into some stacky areas. Okay. So let me give an example now, which is kind of the opposite. So before I was looking at n fields of charge 1. Now I want to look at one field of charge, well, Q, which is greater than 0. Okay, so let me tell you things about this theory and then explain where they come from. So first of all, it has a topological symmetry, a zero form symmetry, an ordinary symmetry, which is exactly the same as before. All that really depended on was the fact that it had a U1 gauge theorem. It didn't really depend on the matter content. So that stays the same. We lose the PSUN flavor symmetry because we've only got one hypermultiplet, so there's nothing to act. But we pick up what's called the electric one-form symmetry, gamma. It's the same type of gamma from the talk this morning. And I'll explain where that comes from, but it's basically the fact that if you look at, that there's a ZQ subgroup of the gauge group that acts trivially on the matter. That's where this symmetry is coming from.
Q means modular.
Yeah. Yeah, I mean, yeah. Yeah, I mean, when we think of it as a symmetry, it's better to think about it as points on a unit circle, and its charge lattice is this thing. But yes. Okay, and again, these symmetries have a mixed Tuft anomaly, which is again the statement that you can't quite gauge them both simultaneously. So let me try to explain where those things come from. Okay, so well, I guess this was already explained this morning. So thank you, Sakura. I'll say a few words about this. So a one-form symmetry acts on line operators. So instead, if zero-form symmetry acts on local operators, one-form symmetry acts on lines. And a basic feature is that if you have a pair of lines, L1 and L2, that admit a non-trivial junction between them, so the picture looks like this, then they must have the same charge under any one-form symmetry. In particular, if you have a line operator that can end, then it must have charge 0, because you can think of it ending as being a junction with the trivial line. So to put it another way, if we're to study one-form symmetries, we're really interested in the lines that can't end, or the lines modulo an equivalence relation, where we say L1 is equivalent to L2 if they admit a non-trivial junction of this type. And in nice circumstances, it's not always true, but in kind of nice cases, you can argue that the set of equivalence classes under this relation form an abelian group, where the abelian group structure just comes from colliding the lines together parallel-wise. And in that case, the one-form symmetry is the Pontryagin dual. It's just a statement that the Wilson lines are the charges, and we want to recover the symmetry. So the symmetry is the Pontryagin dual. Okay, so let's do this example. So the key point is that the fields X now have charge Q. So that immediately tells me that if I look at the Wilson lines, they can, unless they can't end unless n is 0 mod Q. The charge needs to be a multiple of Q in order for them to be able to end. And in particular, if you have a Wilson line whose charge is a multiple of Q, say it's Q times n primed, then it can end on n prime powers of this field X. So what this means is that there's going to be a one-form symmetry, which is ZQ. And if you like, you can think about the equivalence classes of the Wilson lines, which will be labeled by 1 up to Q, or 0 up to Q minus 1. These are the irreducible representations of ZQ. Okay, so there's a one-form symmetry. And there's also a mixed Tuft anomaly. So let me try to explain what that is. So to see that, well, to see Tuft anomalies, we need to turn on a background field. A background field for a one-form symmetry is a two-form. In particular, if the one-form symmetry is ZQ, we need a ZQ-valued 2 cocycle. It's what I call B gamma. And again, the Tuft anomaly is captured by, well, it's captured in this case by basically, again, the fact that these Wilson lines are very closely related to the topological symmetry. They're like these vortex lines for the topological symmetry. And what that means, the fact that those vortex lines for the topological symmetry are charged under the one-form symmetry is a statement of a mixed Tuft anomaly, which can be written in this way. And in this case, you can see it's C1 mod Q, because the one-form symmetry is mod Q. All right. So let me try to tell you what the geometric picture going on is. So in this theory, it's often, well, the Higgs branch is a point. The Higgs branch moduli space is a point. That's the usual statement. But if you sit at that point and flow to the infrared, there's always an unbroken ZQ gauge symmetry, just because the fields have charge Q. So what that should tell you is that it's more appropriate not to think about the moduli space as a point, but actually as a stack that keeps track of that automorphism. So we should really think about the Higgs branch as a stack, the classifying stack of the abelian group ZQ, or point mod ZQ. And just as a very stupid check, well, the equivalence classes of these Wilson lines were the one-dimensional irreducible representations of ZQ. Well, that's kind of by definition line bundles on BZQ. Okay, there's a ZQ equivariant lines on a point, which are just ZQ reps. Okay, so that checks out. We have this picture where we think about the Higgs branch as this stack, BZQ, and we can think about the Wilson lines as line bundles on it in the same way as we did before. And then the symmetries can be understood in the following way, which is the fact that BZQ has a kind of action on itself, which, if I understand correctly, comes from the fact that, well, it's the classifying stack of the ZQ bundles, and this structure is coming from the kind of tensor product of bundles. But, well, suffice it to say that the one-form symmetry ZQ, or really BZQ, acts naturally on this space, which is what we would like. And in particular, the line bundles transform in, as we've already said, in irreducible representations of ZQ. And the statement of the Tuft anomaly is basically the fact that it's only really the trivial line that actually admits a section. That's the only one that can end local operators. Nothing more to it than that, really, in this case. Okay, so now I'm going to put these two together and combine them. Hopefully get something a bit more interesting. But yeah, if there are any questions about this, or otherwise not. Okay. So what I want to do now is to put these two examples together and study now n fields, all of charge q greater than 0. And this is kind of a combination of the two. It has everything together. So in particular, there's a flavor symmetry F, which is PSUN, just like in the first example. There's a zero-form topological symmetry, like both examples. There's a one-form electric symmetry because, again, there's a ZQ subgroup of U1 that acts trivially. But here there's some interesting additional features, which depends on the kind of relative values of the numbers, the integers q and n. Namely, it could be that the flavor symmetry F and the one-form electric symmetry actually combine together to form part of a two group. And that happens if q and n are not co-prime. Oops. I think I definitely mean one. Yeah, thank you. Yes, absolutely. Right. So in principle there can be a two-group symmetry here, which is associated with this short exact sequence. The basic statement is that the two-group will be non-trivial. Well, the two-group is trivial or split if this short exact sequence splits, and that's the case if q and n are co-prime. If they're not co-prime, then we get the non-trivial two-group. And again, just like before, there can be various intricate mixed anomalies between all of these symmetries. All right, let me try to say in a few more details, at least what kind of captures the two-group structure and where this is coming from. So again, we can study the properties of these Wilson lines and what they can end on. So the first thing is that only those operators where n is a multiple of q can end. That's just because we have fields of charge q. So that, for example, if I take the Wilson line of charge q, then that can end on any of the field xj. However, and this is where the group that Sakura called E, or E hat, is coming in. It's only those Wilson lines whose charge is a multiple of q times n, which can end on local operators which are not charged under this center Zn. Or in other words, if they form representations of PSUN, which are not representations of SUN. So for example, if I took the Wilson line of charge q times n, this can end on any any of these fields, xj to the power n, and all of those things transform trivially under the center of SUN because they multiply by a root of unity, an nth root of unity, which becomes 1. Okay. So what type of symmetry you get depends essentially on whether this short exact sequence splits. Okay, here it's good that I have 1 and not 0. So yeah, if the GCD of Q and N is 1, then the 2 group is trivial or split, and the symmetry is just a product of a 0 form symmetry and a 1 form symmetry. But if Q and N share a common divisor, then we get a non-trivial 2 group structure. So what does that really mean in physics? Well, it means that the background 2 form that associated with the 1 form symmetry is not necessarily closed. It's not a 2-coast cycle, but it's equal to something built out of the background for the 1 form symmetry. So a more precise statement is that in the presence of a background for the 0 form symmetry, the background for the 1 form symmetry may not be closed. Rather, it obeys this relation where E is called the Postnikov class, and it's built out of the Box-Jean homomorphism for this short exact sequence. This is the same thing from this morning's talk. Okay, and I'm going to spare you a discussion of the Tuft Anomalies in this case. But there are mixed Tuft Anomalies between this 2 group symmetry and the remaining topological symmetry. All right, so let me then try to give a geometric picture for these symmetries and their anomalies now. Well, in this case, the Higgs branch moduli space, at least what a physicist would call the Higgs branch moduli space, is again, as it was in the first example. If I resolve it, it's the cotangent bundle to CPN minus 1. But again, the idea is that if I sit at any point on that moduli space, close to the infrared, there's going to be an unbroken discrete ZQ gauge theory. And so we want some structure that captures that. And the thing that captures it is by lifting this to the Higgs branch stack. In this case, it's really just in some sense, it's a weighted projective. Well, it's a cotangent bundle to a weighted projective stack. But let me just say it in the following way: it has the structure roughly of a fibration over the moduli space, where all of the fibers are a copy of BZQ. Expresses the fact that there's an unbroken gauge symmetry ZQ at every point. Now, in principle, if I'd have written down some general charges, those fibers could jump around. That's typically what happens with stacks. But this is a special case where the fiber is roughly the same everywhere. And this is sometimes what we call a gerb. So this is a ZQ gerb over the coarse modulus. Okay. So that's the geometric structure. Let me explain roughly where the symmetries come from. Well, it's just kind of a combination of the things in the previous examples. So in particular, the flavor symmetry PSUN, this is the thing that acts by isometries of the base. The 1 form symmetry ZQ, this is the thing that acts on the fibers. And then there's this Postnikov class. And that's Bok of W2. Because W2 appears there, you should think it has something to do with lifting to things being equivariant on the PSUN, because it's the obstruction for that. And indeed, what this Postnikov captures is basically the obstruction to this gerb structure being PSUN invariant. So there's a very clear kind of geometric interpretation of these quantities. All right, we have a similar picture for the Tuft lines. A similar picture again for the Tuft Anomalies. The Tuft Anomalies are basically capturing the properties of the line bundles on this stack and the equivariance properties. So in particular, the Wilson lines, we can think about as line bundles on this stack, just like before. Some of them are fractional, meaning that they don't admit sections. The ones that do admit sections are when the charge n is a multiple of q, but it's only if the charge is a multiple of q times n that those lines can be made equivariant under P of SUN. And that, yeah. Yeah, I don't know, but the simplest way I know how to think about it is if you think about this thing as a quotient. So it's a U1 gauge theory. So if we have so we think about line bundles on a toric variety, for example, I would build them in a very similar way to that. So for example, taking the quotient, we could add a copy of C and let the gauge be back on that with some weight n. Do exactly the same thing here. Good. So indeed, the Wilson lines are line bundles, and they have these properties. And this is basically just a restatement. These properties capture exactly what it means for the two group to have an anomaly. So there's this kind of electric two group, and that has an anomaly with the topological symmetry. And that's captured by these properties of the Wilson lines. I won't write it down explicitly. Okay. You can see that I'm running a little bit fast today, so maybe I'll stop here, see if there are some questions, and then otherwise I'll try to explain roughly what the general picture is. No, that's a great question. Yeah, indeed. No, the gerb is never trivial. So the class is H2 of X valued in ZQ, yes? And I think that I think the class is basically -1. The gerb is never trivial. And indeed, that's a good thing to point out, because another way to think about what the Posnikov class is, E, or how to think about it as an obstruction to lifting to PSUN equivariant gerb, is exactly to start with this class and ask, if someone hands you the gerb with this class, can you tell me what the Posnikov data is? And the way to go about that is via transgression. So I don't think I can explain this here, but you want to take the Borel construction and then pull back this class and push it down via transgression to get a class on H3 BF with coefficients in ZQ. So you want to take something here and map it over here, and you can do that via transgression through the Borel construction. That's the way this story goes.
If you're a number theorist,
Yep.
You said you're writing ZQ.
Yeah.
Some group of
Yes.
so mu.
Okay. Mu, like this. Okay. Okay. Bold funny. Okay. I agree. I think it's actually, I would like there to be a notation that distinguishes between thinking of it as exactly, yeah.
seeing exactly the same amount of cube.
Exactly. Are we viewing it as an additive or a multiplicative
Yes.
group structure? Indeed, yeah. I completely agree. I ought to adopt that notation. Thank you. Good. Okay. Oops. All right. So let me give some conclusions, and by that I'm just going to try to give you a broad type of picture about what goes on in this class of theories. So today I mostly talked about a particular class, very simple class of examples. And I only talked really about one piece of their moduli space. So for these theories in general, and Tudor talked about this yesterday, for theories of this type, they have kind of two, well, they have a very intricate moduli space of vacua, but there are two kind of distinguished pieces called the Coulomb branch and the Higgs branch. And the claim is that in general, we should think about those as Coulomb and Higgs branch stacks in a similar way that we've done here. And that likewise, there are kind of two group symmetries in the same way as in Tudor's talk. There were kind of two types of symmetries, one that act on the Higgs branch, one that act on the Coulomb branch. And the same can be said for these generalized symmetries, in particular these two groups that will act on the Higgs and the Coulomb branch, and they can be captured in this type of way. And indeed, there can be mixed Tuft anomalies between them. Let me say, and finally, as Tudor talked about yesterday, there's a notion of three-dimensional mirror symmetry, which is a duality where you have pairs of theories, very different theories that flow to the same infrared fixed point, but whose moduli spaces, the Coulomb and the Higgs moduli spaces, are interchanged. And so mirror symmetry is something that's going to interchange these structures. And in general, that's a very intricate thing to study. In particular, today I mostly study just the Higgs branch of a gauge theory. And that's a case where this moduli stack always just comes from a quotient. But that's not at all clear for the Coulomb branch side. One has to work much harder. One feature of that is that just like has happened in 5D, where the symmetry enhances at the UV fixed point, in 3D, the symmetry can enhance at the infrared fixed point. And that's part and parcel of the intricacy of studying the Coulomb branch. It's not just going to be a quotient in this way. It's a bit harder to study. Okay. So this was all kind of very special to 3D n equals to 4 theories, but I think that the general ideas, the general kind of picture ought to be a bit more broadly applicable, especially at least to theories with 8 supercharges. And also to theories with less supercharges with some additional features. All right, I'll finish there. Yeah. I think everything should be captured by line bundles. The reason is intuitively, you see that there's always two symmetries here, and the FA acts naturally on X, but you have to also understand how to get FA from the point of view of XB. And there it comes from studying the cohomology in degree 2, or homology in degree 2. And that's something that's very closely related to line bundles. So that's why I think the line.
These line operators
I think that's a fair point. I think the physics of that is when you compactify a theory on a Riemann surface or a space and things like that, then interesting things can happen to the higher form symmetries. Yeah. Okay. Yeah, that's right. Indeed. So exactly. But the ones that are relevant here are the line bundles. So yeah, as you know, it's the statement that, you have a UK gauge theory, even though the gauge group is bigger, the topological symmetry is still U1. It corresponds to the fact that, H2 of the Grassmannian is still Z.
So, in particle physics,
Yeah.
are they the same as the mathematical? We get in pictures.
Ah, yes.
Basis for S3.
I mean, in some sense, yes, but I suspect that in every case when I was using the word multiplet, it was referring to supersymmetry, where the symmetry is not some global symmetry that you would find in particle physics, but the supersymmetry. I think it's roughly the same usage of the word, but in a different context. Yeah, indeed. Certainly lots of the, I mean, certainly the abstract story goes through perfectly fine with some caveats. I think you can do this for 3D n equals to 2 perfectly well as well, provided you've got a kind of, you're in a geometric regime where you flow to a kind of signal model onto the Higgs branch, perhaps up to some discrete gauge symmetry. There you have to worry a lot more about Chern-Simons terms. That's the big thing that comes in. And what that kind of does is it mixes up all these symmetries. You don't get this kind of nice splitting into A and B. Everything gets mixed up together. There are more intricate things to worry about. But I think that the same broad principles will apply. Yeah. Yeah, no, I mean, for me, that was where I first learned about these ideas. So I think yeah, I mean, yeah, particularly the work of Eric Sharp on signal models into stacks. And I think he was the first person to point out the connection of this to these higher group symmetries. Like that. So I've been trying to develop that idea in a very precise setting here. Yeah. Can I say something about the Coulomb branch? Yeah, I mean, actually, the thing. Sorry. Yeah. So yeah, the Coulomb branch has like non-perturbative corrections. It's not automatically a quotient, even in a gauge theory. There are mathematical constructions of it by BFN. So you can build it at least as an algebraic variety. Actually, an algebraic symplectic variety, you can build it as. And you can also understand how to resolve it as well in this picture. So that you have available. And the way that you do, it's kind of hard to explain without loads of details, but the way you build the resolution is actually to realize it as a quotient. So it turns out that there is a little quotient there. And in this BFN construction, when you want to resolve the space, and you can use that quotient to understand the Sacchi structure. So the answer is you can somehow, yeah. Oh yeah, no, that issue is more complicated. Yeah, they're not going to just be Wilson lines, but there's some more complicated. They're like flavor vortices, something like that. Vortices for the flavor symmetry. Question.
Curveball question.
Yeah.
So the Higgs prime of 5 is
Yeah.
also
Yeah.
and 5
Yeah.
How do you think of stacking?
I think that all of like one side of the problem where you have the two group acting on the Higgs stack will be the same, because that's kind of what you would expect, because the electric symmetries don't really care about the dimension. But the story about the other symmetries and the mixed Tuft anomalies will certainly change. So the magnetic symmetry will now be a two-form and things like that. So the story has to change a bit. I haven't thought about it too much, but you know, for example, if you take the theory, you know, SU2 at level 0, we expect it has a two group of the type that we've been discussing. And so I might expect that the Higgs, we would normally say that the Higgs branch of that theory is C2 mod Z2, or a resolution of it. But if there's a two group, I would expect that it should really be a stacky enhancement of that, for example.
But it should also think this next phenomenon of the two forms and change the cost of the two. This is sort of, it should see not just the yes.
Mm-hmm. Yeah. I think so, yeah. I don't know, but yes. Yeah.
Sure.